So yeah, thank you for titling the really good name, that advancing autonomous driving safety. That yeah, we will give you some research insight from our work, mainly from the SAKURA project. So yeah, so the today's talk outline is like this. I will first introduce about JARI, who we are, and then as a representative project, I will introduce about SAKURA project, and also a bit of the traffic data analysis, which is more practically helpful for you. And also, for the third part will be given by Husam, that he will introduce about the human factor and driver behavior analysis in JARI. So let's move on to the first one. So JARI, Japan Automobile Research Institute, is a neutral and public benefit institute established in 1969. So it's almost 56 years to carry out the testing and evaluation of technology-related automobile. We were not a research institute at the beginning. We were started as a testing facility. So we just rented or leased our testing facilities to OEMs, and we just gave the test results to them. But from 1969, we expanded our work also for the research topics, and we are contributing to both industry and society by our research achievement. Now we have about 400 employees, and in our research division, in our autonomous driving research division, we have about 70 members, and 50 of them are researchers and 20 of them are technicians. So our capital is about 1.4 billion yen, which is about 10 million euros. And as I mentioned, our besides our research division, we also have environment research division, which also covers the electrification of the mobility, and a new mobility research division. They are more working on new type of the vehicle and the service perspective of the mobility. And safety, it's a bit misleading that we are also working on the safety, but also the safety research division is also they are more working on a crash or pre-crash safety. And we are located in three locations. One is Tsukuba. This is the main research center of us. And we also have the big test facility in Shirosato. It's about an hour from Tsukuba. And if you go like an hour to the urban side, there's a office also in Tokyo. So in Tsukuba Research Center, we also have a testing facility for the research, and we also have a crash testing facilities, and also some facilities for the EV FC batteries testing, and also not only about the hardwares, we also have the softwares or something in the middle where to test like balloon target, VRU dummies. And also, we also have the driving simulator, which will be presented by Husam, I guess, later. And not only about the hardware testing or real testing, but we also working on some simulation topics. And in Shirosato Test Center, this is quite big facility. That overall length of the high-speed road is about 5.5 kilometers. And there are many types of the testing, but usually we are not able to use it because usually this is used for the rent, and most of the time OEMs are using it. And as far as I know, this part of JAR is making most of the money. And from the perspective of the research seat of our research division, we are mainly working on four parts. One is about the safety evaluation methodology of ADS. So we are trying to quantify the relevant exposure of the to the risk. So by analyzing the traffic data and patterning, And also, we are trying to define how well should ADS behave. And this result is also reflected to UNR 157 as a competent and careful human driver model. And another part is that we are also working on human factors and modeling in automobiles. I think this was more core part of our research division before ADS comes, that we evaluate the driving performance in both in test track and simulator. I think that's the good advantage of JARI. And another thing is that we also evaluate the ADAS feasibility through testing and also through the simulation. And not only the real testing, but we also do some modeling because our government is also pushing the digitalization of the development. So to help industry, we are also building the simulation model of the ADS or ADAS for efficient development, which includes some sensor modeling. And not only modeling not only the model in a simulation platform, but we also do the testing. That's also important part of our work, that to verify or or validate the model. And also traffic simulation, and not only about the microscopic analysis of the vehicles, but we also do some traffic simulation in macroscopic to evaluate the safety impact. For example, when ADAS is deployed in some penetration rate, we don't know how much does it affect or influence on traffic in a macroscopic point of view. So before it comes to the market, we can also evaluate with the traffic simulation. And other hand of the research, we also need to consider about the needs from the society. And this I just rephrase in a gentle way that it's more on about the funding, but yeah, basically we have three funding source, and also we do internal research for the kind of future investment. So first one is a government-funded project, which also include the SAKURA project. We usually targeting on standardization and regulation as the outcome output of this project. So the government support us to help industry to accelerate Japanese market, and also support us to regulate in a global manner, to not to regulate too much, to not to limit industry's work. And another key is the JAMA commissioned researches. I will explain about the JAMA later a bit. Well, usually we have common research issues from OEMs, and about 50 topics per year is conducted, and output usually aims on the standardization or guidelines from the industry. And also we also work for each company that as a contracted researches and testing. So we do research and testing for individual companies or academias, and we also do the testing of the certification and assessment testing like NCAP or JNCAP. So for those who don't know about the JAMA, I will explain a bit about it. So JAMA is a Japan Automobile Manufacturer Association, which is a non-profit industry association, comprises 14 manufacturers of passenger cars, trucks, bus, and motorcycles. And we are comprehensive research institute, carries out basic surveys, research, technology development, testing and evaluation technology related to the automobile. So in short, JAMA represents the opinions from the automotive industry, and JARI, we support JAMA to provide scientific evidences. So that's the quick introduction of JARI, and then let me introduce about SAKURA Project from now on. So SAKURA Project is a funded by Ministry of Economy, so expected to support Japanese industry to accelerate the deployment of ADS. And this project aims on establishing a continuous safety ecosystem, a safety evaluation ecosystem for safer AD development. So the ideal goal is shown like this, that so we expect that each company will develop new ADS and they will validate the system. But what's the difference from the conventional development process of the V model is that ADS cannot be developed only in one way. We consider that the feedbacks from the real world data is important. So for the beginning, we provide the scenarios to develop the ADS, and also we collect the data as a scenario and making the loop. In this circulation, we consider it will help the safer and safer ADS development. And it is also important to coordinate the standardization activity. Otherwise, we can only sell our car in Japanese market. So we developed this scenario-based safety evaluation framework, and also we try to input into the international standardization. So to achieve this, I will go into a bit of this project. So first, let me start from the really high-level requirement of ADS, that according to the UNECE WP29 framework document, it says the automated vehicle shall not cause any non-travel risk, meaning that under their operational domain shall not cause any traffic accident resulting in injury or death that are reasonably foreseeable and preventable. So to specify this requirement, we first divide it into two axes. One is about defining the foreseeable boundary, and the other one is to define the preventable boundary. We consider it is a kind of independent factor of requirement. And to define this more in specific, we structurize the safety argument as this flow. So the top goal is, of course, the social acceptance, well, or at least certificate by the government. And to achieve the requirement from the WP29, or also including the requirement from the WP1, which is about the traffic rule compliance, we set the two factors in under the social acceptance. And well, I will not go into detail of this traffic rule compliance here today, but the main contribution of Sakura is on left side, that we try to define the free of unreasonable risk. And also about the risk, there are three main features. One is about the cybersecurity, which is external threats, and the other one is another one is functional safety, which is usually defining about the system failure. And even in intended functionality, there are still some risks. So our work is going to detail of this part. And first, we define the dynamic driving task of ADS, and then within ODD, we try to define what is reasonably foreseeable and what is preventable. But still, it's really big work to define the reasonably foreseeable situations and to define the preventable accident in a comprehensive manner. So we just limited our work more in detail, that we more focus on a critical conditions, which means when some risk has explicitly happened, we try to model that kind of scenarios in comprehensive manner. and then define what is preventable and what is not preventable in that condition. So our goal is to define scenario catalogs in this critical condition. And for each scenario defined in a catalog, we try to define reasonably foreseeable parameter ranges and also preventable ranges. And from here, I will explain about what is scenario catalog. So first, to define the scenario catalog, we divided driving task into three independent tasks: perception, judgment, and control. Or in SOTIF, it is defined as a sense, plan, act. So this might be more easy understanding word, but yeah, at the moment we developed this structure. The SOTIF was not published, so yeah, maybe we will rephrase it later. And for each perception, judgment, and control, for each task, we defined critical situation. And then by combining the three tasks, it is defined as a scenario to be evaluated. And this framework is also reflected in ISO 34502. So first, we'll go a bit about the perception scenario, which is defining the safety critical scenario by causal factors and sensor principles. Well, it's a bunch of the list, so I'm not going to detail it, but basically, the idea is that we have defined the scenarios for camera, LiDAR, and radar, which is the main component of the perception in current ADS or even ADAS. And for the next one, well, I will skip the judgment and first go to the control. That scenario is divided into, for the vehicle stability disturbance scenario is divided into two categories. So as you know, on a vehicle dynamics, that external force is applied only on a tire or a body. So we divide it into two parts as a vehicle stability disturbance, and we listed the whole, the factors which can affect on ADS control performance. And the last most contributed of JARI is about the traffic disturbance. So traffic disturbance scenarios organize and combine the physical factor related to the safety. So we extract exhaustive and finite number of the scenarios. So by considering the road geometry, ego vehicle behavior, surrounding vehicles location, and surrounding vehicles motion, we listed the whole interaction patterns in some abstracted level. So this is the result of the functional scenario catalog that we categorized interaction with other traffic participants into 58 car-to-car functional scenario patterns and 8 car-to-pedestrian, which is a representative of the vulnerable road user, as 8 functional scenarios. And we consider that all patterns on the road, public roads, are covered with this catalog. But of course, when it goes into the detail, we need to specify more in detail. But in a high-level scenario abstraction, we consider this represent the whole interaction patterns. So as you might see, we define intersection as one road geometry, and there is no roundabout is listed in this catalog, but we consider the roundabout that is a subcategory of the merging or branch. So if we parameterize it and if we consider the curvature of the road geometry, then it could be also covered. Oh, sorry. And I think I've already explained about this. Some achievement from Japanese expert is reflected in ISO 34502, and Yeah, from now on, let me go into a bit detail of defining reasonably foreseeable range. So, once we define 58 functional scenarios, still we need to do some work to define what is reasonably foreseeable. And for the definition of the reasonable foreseeable, we consider that is that a relevant exposure in a real traffic. So we consider that if the situation is something not frequent, but still it could be happen in some time period, like 1 year, 10 years, and then we consider it as a reasonably foreseeable. So it's not like all derived from the human knowledge. That so if well, yeah, if you consider like the something will fall from the sky, yes, still you can imagine that, but still we consider that it's not foreseeable. It's just the those kind of the situation could be excluded by calculating the statistics. So to define the reasonable foreseeable logical scenario for one of functional scenario listed in a previous slide, first we collected the data. So we collected the data from the vehicle and also from the fixed location camera. We somehow normalize the data into the vehicle behavior data. So first the data collected from the vehicle is driven on many types of the road, and there are many types of the curvature. But to make it simple, we stretch the road and converted the behavior into the coordinate along the road to make the vehicle behavior more simple and also easier for statistical analysis. And then we made a rule for extracting the target scenario scene. For example, in case of the cut-in, we define as once the adjacent vehicles start the lateral movement, and then this vehicle comes in front of ego vehicle, it is considered as a cut-in. That's just an example. And then we also calculated the parameter distribution, and also we consider some correlation in each parameter, and then finally we model the reasonably foreseeable parameter range. So for example, of the cut-in scenario, we define four parameters. Well, the limitation of this defining the scenario is that there are a bunch of the parameters. If we consider like acceleration, it could be integrated, but to make it simplify the model, we want to minimize the parameter as less as possible. So first we analyze the independent component of the scenario parameters, and then we selected 4 parameters in cut-in scenario, and then we define the maximum and minimum of each parameter, and then also calculated the distribution. Well, yeah, just to keep up some time for Husam, I will just skip some slides. And yeah, as a result, this is an example of the correlated parameters occurrence probability shown for the cut-in, that this horizontal axis represents the relative velocity, so which means other vehicle is coming closer to ego vehicle, and this represents the distance, and the vertical represents the frequency. So when the blue becomes darker, which means it's more rare case, which can be possibly excluded from the reasonably foreseeable parameter range. And also by converting this to the expected exposure in the annual driving, by making some assumption, we calculated the annual exposure frequency from the data. So this is a remarks from SAKURA Project. Scenario-based safety evaluation framework is developed in our project, and international harmonization is also a key activity of the project. And well, what I couldn't explain, human driver analysis is also important. Even the target is ADS safety. And Husam, I guess you will catch up with the human factor part.
Will present two of our studies that is related to human factors investigations. So my colleague, Dr. Hiroki, presented our activities from systems safety assessment point of view. And my part will be presenting from users' point of view. So these two studies investigate about what makes drivers disagree with automation, and this is a human factors investigation into driver interaction, focusing on level 3 conditional automation. So this is just brief and fast introduction about level 3 conditional automation. Is that it is a system that's able to perform the entire dynamic driving task that include lateral and longitudinal vehicle motion control, which means hands, feet free. And also the system is able to perform the object and event detection and response subtask of the dynamic driving task, which means driver can take their eyes off the road. Some systems are also capable of bring the vehicle into minimal risk conditions that reduce the risk when the trip cannot or should not be completed. So what is the position of conditional driving automation? So this system represents the borderline between driver assistance and automated driving. So for level 3, for level 2 partial driving automation, although the system can perform the lateral and longitudinal driving task, and also some part of the object and event detection and response, drivers are not allowed to take their eyes off the road. They should always monitor the road, so it is not considered as automated driving system. So starting from level 3, then we can explain about the, or we can name the term of automated driving system. Why we choose automated driving system for our human factor investigation is that there are several contradictions with the use of level 3 automated driving, which is that the system can perform the entire dynamic driving task, as we explained, but the system may not do so in some highly critical conditions, such as bad weather conditions or some complicated crash scenes. Also, the drivers may not monitor the driving environment, but they have to respond to a request to intervene when issued by the system, and also respond in system failure situations that includes silence failure that have already been investigated. So drivers can also enjoy any activities they like, but they may not fall asleep or leave their seats, which can easily be misunderstood by the users of such systems. So these contradictions make the human automation interaction is highly critical for safety and for the performance of conditional driving automation. So so many studies have investigated how driver responds to system failure and the request to intervene, before request to intervene, after request to intervene. However, few studies have examined driver or user interaction with such systems in situations that can be handled by the system. So our studies aim to investigate driver interaction with conditional driving automation in urban environment where the system can handle the situation. And also it aims to compare human and automation performance in identical scenarios. And also we aim to investigate the effect of mismatches between driver perception and system action on the driver emotions toward the system. So in order to address these aims, we need to choose a scenario. So we decided to go over the literature to pick up a scenario that can address these questions, and also it can be more, how to say, international, not specific to a country, and also we thought that it should be also representative in terms of criticality and the number of crashes that's involved for such scenarios. So we went through three main scenario catalogs. One that is Sakura Urban Scenario Catalog, that is based from Japan, that is based on experts' on opinion to extract scenarios from traffic disturbance, road geometry, and vehicle behavior, and come up with 58 functional scenarios. And we also went through NHTSA, pre-crash scenario topology, that extracts 37 scenarios from 6 million light vehicle crashes. We also reviewed the IGLAD codebook that extracted 311 functional scenarios out of more than 8,000 crashes from 12 European countries. So we pick up the scenario of overtaking with oncoming traffic that is common among the three scenario catalogs from Sakura, NHTSA, and IGLAD, and it represents a high number of crashes based on NHTSA and IGLAD codebook. So why we choose this test scenario? We choose this test scenario because the automated vehicle we can investigate the automated vehicle from both sides. We can investigate the automated vehicle from the side of the party which initiates the overtaking. So the automated vehicle, we assume that the automated vehicle initiates the overtaking. And also we can investigate from the side of from the responder side, when we assume that the automated vehicle respond to another vehicle initiate an overtaking from the opposite direction. So we will represent the two studies that is implemented in driving simulator at Japan Automobile Research Institute, showed in this picture. So we conducted two studies where the system initiates the overtaking, and when the system responds to the overtaking from the opposite direction, we implemented level 3 conditional automation in this experiment. So also in order to investigate how the automated driving system should safely respond to such scenarios, we modeled the system based on the behavior of three professional drivers that is considered as competent and careful drivers that were exposed to the same driving conditions. So first, we modeled the system based on professional drivers and not just randomly selected behavior for the system in such scenarios and consider it as safe. So in the first study, that in the system that initiates we propose that the system initiates the overtaking. We investigated this scenario. This is the black is the automated vehicle, and we assume that automated vehicle in the presence or absence of leading vehicle approach a stopped vehicle in the middle of the road while there are oncoming traffic from the other side, and then the automated vehicle approach, decelerate, and start an automated overtaking of the stopped vehicle based on the oncoming traffic, whether there are oncoming traffic or no oncoming traffic. And then we come up with some results that I'm going to present later. So we provided the HMI examples for the drivers, for the users of conditional automated driving in such situations. So as you can see that the HMI that is provided to the drivers are kind of detailed HMIs that shows the surrounding traffic conditions and also the system behavior, in addition to sensors that shows the risk to the users. So it can be considered as a kind of detailed HMI to be provided to the participants. These are just examples of HMI that's provided to the participant in different situations. So interestingly, although the system can handle the situation safely, and the system did not issue a request to intervene to the participants, around 50% of the participants decided to override the system, decided to intervene, even without being requested. So as you can see in this figure, most of that represented the number of overrides in each scenario. Most of overrides occurred in scenarios where there are oncoming vehicle approaching on the opposite directions. So the participants, they were concerned when they recognized there are vehicles in the oncoming direction and the system is approaching or attempting to make an automated overtaking. So they interrupted the system, although the system did not issue a request to intervene to the participants. Where this intervenes occurred. In the scenario, we can, as we can see from the results, 50% of these intervenes occurred during the approaching phase, when the automated vehicle approached the stopped vehicle. More than 30% of these overrides occurred when the system attempted to override, to start the overtake or lane change to bypass the stopped vehicle. 5% occurred during the passing phase, and 12% occurred during the returning phase, while the system attempted to return to the original lane. Maybe because the drivers, they were scared because they are seeing the oncoming vehicle from the other direction, so they try to override the system and bring the vehicle as fast as possible to its original lane to avoid a possible collision. And as you can see from the results of overtaking time, usually drivers who override the automated driving, they finish the overtaking maneuver faster than the system. Maybe also because they were concerned about using the opposite direction lane. From the results from about the time headway, we can see that drivers kept longer time headway and safer performance than the system as they perceived. From the steering behavior, we can see that the maximum steering angle maintained by the driver was significantly larger than the system, which means that the system performed smoother overtaking maneuver compared to the driver, also again because maybe they were concerned about using the opposite lane. And then we freely listened to the participants' opinion about the system. More than 50% felt that they are safe and satisfied about the performance of the system. 42% they felt safe, but they have some concern. And 7% felt unsafe and unsatisfied. So interestingly, although 50% and 40% they felt safe, there were more than 50% of the participants who override the automated driving system. So it means that the overrides was not only related to safety. So from about the other study that's in which we investigated when the system exposed to the another vehicle initiate an overtaking from the opposite direction. So we investigated.
Sorry to interrupt for a bit. Just to note, for a couple of minutes left, and then we have about 5 minutes left for a couple of questions at the end.
Okay, thank you very much. I'm sorry to exceed the time. So I'll go quickly about this study. So we make the system, the automated driving system, exposed to different overtaking maneuver from the opposite direction, and we investigated also driver behavior, system behavior. We provided simpler HMI as the participant from previous study complained about the detailed HMI. And then we can see that from the number of crashes, we can see that the automated driving system was able to avoid all crashes, while the participants involved in several crashes, especially in the third scenario, that's more critical scenario. From the I'll skip some slides, and I will show that is interestingly in scenario 1, where the risk was less, the drivers performance was safer than the system. As the criticality of the scenario increased, the system behavior start to be safer than the system and able to avoid the yellow zone, that is near crash zone and crash zone. And I'll skip these slides, and I'll go to the maybe final key findings that come from we obtained from these two studies that related to driver trust in automation when its behavior align with their expectation of safety and human like driving. And also system must, while the system must ensure safety, they should also balance comfort, responsiveness, and transparency that's related to HMI to improve the human system interaction. Requires not just reliable automation, but also synchronization between driver perception and system intent. And as a key takeaway, by aligning system decisions and human expectation, conditional automation can achieve both safety and acceptance in urban environments. That's the key findings from the two studies. Thank you very much.